RingCentral, Zoom, and Nextiva are rapidly bundling advanced AI voice capabilities directly into their core telephony suites, setting a new baseline for what customers expect. This creates immense churn gravity for smaller managed service providers and regional UCaaS operators. An inability to offer intelligent call routing or AI reception risks bleeding clients to these larger ecosystems. But introducing AI into legacy infrastructure like NetSapiens, 3CX, or Free PBX presents a severe engineering dilemma. Providers need the functionality, but they cannot afford to rip out their established installed base to get it. The barrier to deploying AI voice agents is not an AI modeling problem, it is a SIP signaling incompatibility problem. We are going to examine exactly why traditional AI integration fractures existing call routing and demonstrate how a SIP bridge architecture solves this by acting as a native PBX endpoint. Telecom modernization depends on keeping the PBX as the definitive routing brain, while securely attaching AI to the network edge. There is an assumption that modern AI platforms easily connect to a PBX because they quote-unquote speak standard SIP. This table maps the actual telephony capabilities across the leading AI agent platforms. It reveals a highly fragmented landscape. VoPI utilizes a trunk-first design. It requires engineers to bring their own SIP carrier support to route calls. LifeKit explicitly notes in its documentation that SIP register is not supported at all. Bland and Ratel offer varying degrees of explicit SIP integration, yet they still lean heavily on trunking and external carrier workarounds. For engineers attempting direct integration, this means the connection model must be completely rewritten depending on the AI vendor you select. Because native extension registration is rarely supported by default, dropping an AI agent directly into a PBX environment is structurally impossible without an intermediary layer. When native registration fails, providers standardly rely on the traditional AI voice integration architecture. Under this model, an inbound call hits the PBX dial plan and is immediately forced back out to an external carrier to reach the AI agent. This external routing path introduces an immediate operational penalty. The provider is forced to rebuild their established dial plan logic to accommodate the detour. It also introduces external carrier dependencies, frequently requiring providers to port existing numbers just to get the routing to function. Beyond the routing headaches, this design creates notable security compromises. Relying on shared server, IP-authenticated trunks exposes the network to broad vulnerabilities unless unique termination URIs are perfectly implemented. Maintaining basic media security in this trunk-centric model demands stringent IP allow listing and constant manual firewall management. Utilizing traditional external trunks forces the MSP to forfeit network control, compromising both security and internal routing logic strictly to enable an AI feature. This diagram shows the structural alternative, the SkipHold call flow architecture. The SIP bridge serves as a translation layer sitting between the legacy PBX and the modern AI pipeline. Looking at leg 1, the bridge connects directly to the provider's existing infrastructure. On this side, the bridge speaks classic PBX SIP. It authenticates as a standard, credentialed internal endpoint, bypassing the need for external trunking entirely. Moving to leg 2, the bridge automatically translates that internal signaling into the required WebRTC or telephony API format. The inbound caller hits the PBX, and the PBX routes the call directly to the AI extension via the bridge. The tactical advantage of this flow is that the existing routing logic remains completely intact. Complex IVR multi-language routing, ring group failovers, and timeframes operate exactly as they did before the AI was introduced. This native connection also secures the mechanics of call escalation via SIP refer. The bridge standardizes these refer requests. If a caller needs a human, the AI agent can seamlessly transfer the call back into the correct queue without dropping the connection. Crucially, the bridge maintains the network's baseline security posture. Cryptographic standards are preserved end-to-end, including TLS signaling, SRTP audio encryption, and stir-shaken identity headers to prevent spam labeling. By acting as a normalization layer, the SIP bridge transforms an otherwise incompatible external AI service into a secure native PBX extension. This architecture establishes true agent platform agnosticism. When the underlying AI vendors behind the bridge need to be updated or replaced, the physical telecom infrastructure is undisturbed. Because the bridge handles all API translation, an operator can swap a VAPI node for a retail node without rewriting a single PBX routing rule. This approach insulates the core telephony network from the volatility of AI startup life cycles. For managed service providers and UCaaS operators, this technical architecture directly drives commercial outcomes. Compared to traditional models, the bridge approach eliminates number porting, preserves routing, and keeps the provider at the center of the service delivery. Preserving the network state allows providers to deploy white-label AI receptionists as a high-margin overlay service. It offers feature parity with massive enterprise bundles, defending against client churn while the provider retains complete billing control. A SIP bridge turns a complex, risky infrastructure replacement project into a secure, profitable, native extension of the network you already own.